In this lecture, we'll do algorithm analysis of our ordered dynamic array class. Remember, the ordered dynamic array is a child class of dynamic array, so we don't have to do our algorithm analysis again on those operations that are contained in the parent class. We do need to do an analysis of the operations included here, so we'll start with add. Again, we have that expand that's order n, so we may end up with order n, but remember it could always be worse also, so we have to check for worse, and we take a look at this while loop, and we determine how many times this while loop will execute in the worst case, and in the worst case, we need to add the item at the very end of all the valid elements in the array. So this while loop could, in the worst case, execute n times. And incrementing add location is a constant time operation, but that means that the while loop is order n as well. We also need to consider what shift up could be. And shift up could be order n in the worst case, but that's only if we actually need to insert the new item at the beginning of the array. So the worst case here is exactly the opposite of the worst case here, because if we're adding the new item at the beginning, then this while loop doesn't execute at all. So the combination of these two things is actually order n. And this is constant time, and this is constant time. So basically what we have is order n plus order n plus some constant time stuff. And that means that this would essentially be 2n, but remember we throw away the numbers when we're talking about algorithmic complexity. So adding is actually order n. Removing, we need to go look at index of and figure out its algorithmic complexity. This is kind of tricky to do. So the big idea is that we are chopping the array in half each time we're looking for the item. So in the worst case, this while loop executes log base 2 of n times. And everything inside here is constant time. So that means that this chunk, the while loop and the loop body, executes log base 2 of n. And remember, we regularly just say log n when we're talking about algorithmic complexity. So this is log n. That means the index of operation is order log n. Coming back up to remove, we now have an order log n operation. This is constant time, this is constant time, these are constant time, but we have the shift down operation here, and we need to go evaluate the algorithmic complexity of shift down. So we need to consider the worst case here. What's the worst case for shifting things down? The worst case is, in fact, if index is 1, which means that we're going to shift everything down. We're removing the very front element in the array. So we have to shift n-1 things down. And that means that this for loop executes n-1 times, which is order n. So the shift down operation in the worst case is order n. So back up here and remove, this contributes order n to the complexity. So we have an order log n added to constant time, order n, constant time, and constant time. So essentially we have order log n plus order n, but we can get rid of the order log n term because as n gets large, the order n term dominates the order log n term. So we always take the highest order term in our algorithmic complexity, and that means that the remove operation is order n. Before we finish this lecture, you should do an in-video quiz, and the answer is sometimes the ordered dynamic array operation is faster, like index of is log n for the ordered dynamic array because we can do a binary search versus order n for index of the unordered dynamic array because we have to do a linear search. Sometimes it's the same because remove was order n for both, and sometimes it's actually worse. And so when we add to an ordered dynamic array, that's order n, and when we add to an unordered dynamic array, while we do know it's order n in the worst case when we have to expand the array, it is commonly constant time, order 1, instead. To recap, in this lecture, we got more practice doing detailed algorithm analysis on C# source code.